Hiya. Today we're going to have a look at some patterns in algebra. We're going to look at a very simple matchstick pattern, and we're going to come up with an algebraic rule, but really understand where the rule comes from. So the one we're going to look at, these type of matchstick patterns are very popular in school, and the questions we're going to ask are very generic questions. They're the sort of questions you always get asked when you do these type of patterns. The first one is how many sticks are in the next diagram. So it's just a continuation of the diagram to make sure the person can actually follow exactly what's going on. The next one they often ask is to find how many sticks are there in a diagram that's further on down the pattern. This is normally can be done with brute force, but if you can come up with a more clever way of doing it, then so much the better. And the last one is to write an algebraic sentence, that is like an equation, to describe this system. We're actually going to do this upside down. We're actually going to create the algebraic equation right at the start. But to do that, we're going to have to actually understand the pattern that's going on. So this is a table that I've done up, and it's just describing numerically what's actually going on here. So we'll notice on the left-hand column is the number of squares in each diagram, and on the right-hand column it's the number of matches. So for one square there's 4 matches, 2 squares 7 matches, 3 squares 10 matches. Now to find out how many's in the next one, you could just draw it, which is fine, doing it using a diagram, and then count it up. You may actually notice on the right hand column though that it goes 4, 7, 10, that they're constantly adding 3 per square. So when there's a new square on there, you're adding 3. And so they'll just continue the pattern and say 13. So that's fine, but if you're asking what it is for the 10th diagram, that is 10 squares, you can do it by just following the pattern. You just get add 3, add 3, add 3, add 3 until you get all the way down to 10. So that's fine, but in order to know the 10th one, we need to know the 9th one, so we can add 3 to it. But to know the 9th diagram, how many matches are in it, we need to know the 8th diagram, and to know the 8th we need to know the 7th, and so forth and so forth. And so what happens is this type of rule, this one where you need to know the one before it, it's called recursion. It's a recursive rule. It's the way Fibonacci numbers are described. The limiting thing about recursion is that in order to know a particular term, you need to know at least the one before it. And that's very limiting because you need to know all the ones before it. It'd be great if we could actually just jump straight to the answer. And so that's the benefit of the rule that we're about to try and derive, is that we don't need to know any other terms. Once we've got the rule, we can jump to whatever number we want straight to it without ever having to know any other terms before it. So here we go, let's try and derive this. I'm going to write the numbers 4, 7, 10 in a very different way. I'm going to break them down, and I'm going to break them into certain numbers because of the way the diagram is created. So here we go. I'm going to put those aside, and let's have a look. The first one, you could actually write 4 as 3 plus 1. Now why am I doing 3 plus 1? Well, if you have a look at the diagram on the left, you'll notice that there's always one match and then 3 around it. Now I haven't done that by accident, I've done that because that pattern continues throughout the diagram. So watch the next one, and here we go. So this one is actually 3, the same ones that we had before, the white one and the yellow one, but now we've got 3 more. And so we're actually going to do the same with the next diagram. So we've got what we had before, and then there's 3 more. And you can actually start to see a pattern in the numbers that there's this constant 3 adding, like we saw before. But there's a way that you can actually abbreviate this plus 3, plus 3, plus 3 stuff. So here we go. The first one you can actually say is one group of 3 plus 1. The next one, remember this repeated addition is actually really saying multiplication. That you've actually got 2 groups of 3 plus 1. And the last one, you've got 3 groups of 3 plus 1. But remember, 1 group of 3 and 2 groups of 3 and 3 groups of 3, that's just saying multiplication. So I'm going to rub it out and I'm going to put in 1 times 3 plus 1. And then the second one, we're going to say 2 groups of 3 plus 1 is actually 2 times 3 plus 1. And the last one here, 3 groups of 3 plus 1 is actually 3 times 3 plus 1. Well, as you can tell, there is a rule. There is a rule here that is linking. There's a pattern that's going on. And if you notice, the number of groups of 3 there are is the same number of squares there are. If there's 3 squares, well then there's 3 groups of 3. plus 1. If there's 2 squares, there are 2 groups of 3 plus 1. And so now we can actually make a rule that this seems to be the number of matches is equal to the number of squares times 3 plus 1. And this is a rule that seems to work for all of them. And so if we go back to our question now, we've actually created this rule. So how many sticks are there in the next diagram? Well, we know that there's 13. How many sticks are in the 10th diagram? Well, we figured out that rule, that it's the number of squares times 3 plus 1. So if there's 10 squares, the 10th diagram, then it's 10 times 3 plus 1. So it's 31 matches. I can jump straight to the answer without ever having to know what the 9th diagram is or that. And so finally an algebraic sentence is to describe a system. So the number of matches, which I'll just call M, is equal to 3 times the number of squares plus 1. Folks, I hope you've found this little quick video helpful. That these rules are not just random, they're not plucked out of the air, that there is a good solid logic behind it, and it's a logic and a reason that anybody can understand. All the best, folks. Bye.